So just like when we talked about our overview of lipid metabolism, we're going to sort of have this funnel approach to thinking about protein metabolism. And that's because we can have protein that comes from exogenous sources, or that's really our dietary source. So exogenous or dietary, right? And then we've got endogenous sources. And that's really enzymes, tissues that are degraded, so forth. So enzymes, other tissues that we're breaking down. But at the end of the day, no matter the source, exogenous and dietary, endogenous as in internal sources, once you get to intracellular amino acids, there's not going to be a distinction in terms of how we metabolize this, right? So we need to talk about degradation of endogenous sources, and then we need to think about digestion, uptake and transport of dietary sources. So digestion, uptake, and transport. Now, we're actually not going to say too much about this beyond the digestion piece, because once you get those digested free amino acids into your bloodstream, really we don't have the transport issues like we did with lipids, where we can't have those hydrophobic substances sort of floating around in our circulatory system. They have to be compartmentalized and trafficked with a lipoprotein. So we don't have that sort of transport issue with amino acids or with carbohydrates because they are so hydrophilic. But again, once you have these intracellular amino acids, reminding us of the generic structure of any amino acid, okay? What we're going to talk about is how we sort of break down these different parts, okay? So we're going to have sort of this amine group here, okay? And this amine group, we're going to call this an elemental problem, and we'll revisit this in some detail a little bit later. Play on words is intentional there. We have that nitrogen that we have to deal with. So we've got our elemental problem. And then we need to think about how we metabolize the amino acid nitrogen, right? Carbon, hydrogen, and oxygen. It's easy to think about what happens with those in our fuel equation. Fuel with carbon, hydrogen, oxygen ultimately becomes carbon dioxide and water. Nitrogen, we need to think of something different to do with that, and that's going to be the urea cycle and the production of urea. So we're going to get to that in a future video. And then once we take care of that nitrogen part, then we're going to have the rest of this part. Okay? And this is really the alpha keto acid skeleton part. So once we deal with the nitrogen piece, the piece that we have left here is an alpha keto acid skeleton. So an alpha keto acid skeleton. And the question really is, who do you look like? Okay? If you end up looking in some way or can be converted into pyruvate, you are then a glucogenic amino acid. If you resemble or can be converted into acetyl-CoA, then you are a ketogenic amino acid. Okay, so ketogenic amino acids, again, being able to be converted into acetyl-CoA, sort of have an end fate of either being fully broken down in the citric acid cycle and being made into ATP, or being synthesized into ketone bodies in a need state, or in a fed state. And I probably should have left myself a little bit more room here, so let me make this arrow a little bit smaller and move my stuff around. Okay, so again, acetyl-CoA can be made to, in a need state, ATP or ketone bodies if you're the liver and can circulate those as a hydrophilic circulating fuel. But if it's excess acetyl-CoA, any excess acetyl-CoA, whether it's carbohydrate in origin or amino acid and protein in origin, will be synthesized into triglycerides. Glucogenic amino acids, on the other hand, right, they can be converted into glucose. And the key here that we have learned is that acetyl-CoA cannot be made into glucose. So if you're going to be making glucose, again, by gluconeogenesis, you need to have glucogenic amino acids to do that. Ketogenic amino acids are excuse me, designated to be only made into ketone bodies as a hydrophilic circulating fuel. And so there's no ability for those amino acids to be converted into glucose. Okay, so now what do we want to think about in terms of sort of next steps or next pieces, right? I want us to think about proteins and amino acids as existing in sort of a substrate cycle. So we're going to think about proteins and amino acids as basically part of a substrate cycle. So we've got a catabolic arm, where we're basically breaking down proteins into their cognate amino acids by breaking and hydrolyzing those peptide bonds, or we can be building amino acids into proteins in an anabolic fashion, right? So thinking about this as being a substrate cycle. Remember, substrate cycles are basically just interconverting different metabolites, generally operating in catabolic and anabolic fashions. And so there's several things that we can think about that we do with these amino acids. We highlighted that if they are in excess, so if we have excess amino acids, right, they are going to be metabolized, and the caloric value is at 4 calories per gram, right? But that's not the only reason that we consume proteins, right? And I should say the intent of protein consumption is not to be converting them into fuel at 4 calories per gram, right? The intent is some of those amino acids might be used to make other metabolites. Okay, lots of different metabolites have an amino acid origin, okay? We also can be using them to make glucose, right? Again, if they are glucogenic. Okay, and I should say that not only can we make these into metabolites, we can make them into other proteins. So this arm is really the building block arm. Okay, making them into other metabolites or proteins, but it's also a building block to make glucose. Okay, so the last little piece to sort of wrap up on this video is to think about if we've got these endogenous proteins. Like, why would we need to be breaking down our own internal stores of proteins, right? So these are going to be reasons to break down endogenous proteins. Okay, 3 reasons to talk about. Okay, the first is maybe there's a malfunctioning protein that we need to eliminate. So maybe we need to eliminate a malfunctioning protein. Okay, and it might not be malfunctioning in that it's bad. Maybe it's malfunctioning, or maybe we'll say malfunctioning or unneeded. Okay, because one of the things that we'll talk about is things like uterine regression, right? Pretty amazing story to think about. At childbirth, the uterus weighs, about 2 kilograms, and in the course of about a week and a half, it shrinks down in size to be about 50 grams. So significant sort of destruction internally of that tissue, of that protein, and that kind of is an idea of eliminating something that's not needed in your body. We also can think about it as a way of sort of metabolic regulation. So we can have metabolic regulation by availability. So via availability. The main way that we've talked about controlling sort of the biochemistry in our body by enzyme sort of activity is, controlling the activity of those enzymes by covalent modification, adding or removing phosphates, allosteric regulation. But the idea is not creating or destroying that enzyme from scratch. It's taking that enzyme and turning it on or off, right? So again, this is versus that activity control. That activity control is really on versus off, okay? Where availability is present or absent. So by regulating sort of the increased degradation of proteins, we can sort of control that availability. Okay, so eliminating things that are not needed or malfunctioning, we can sort of control metabolic pathways by controlling the availability of enzymes versus talking about the activity piece. And then the third thing is, sometimes we do need to tap into that reserve if we are fasting. So proteins in our body provide that unintended but important reserve when needed. So a reserve when needed. And specifically, we're going to address this when we talk about fasting. So the importance of being able to tap into those building blocks when we are not consuming them in our diet, and we still need to have those building blocks to do things like generate metabolites or other proteins that we need, or maybe we need to use that as a way to help regenerate glucose when our reserves are tapped out.